Okay, day 3, exponential and logarithmic functions. Let me try to explain logarithms in a way that hopefully you'll understand. In grammar school, the most important skill that you learned was how to read, because that unlocked the world of words to you. I'm hoping if I teach you how to read logarithms, it'll unlock the world of logarithms to you. So, here, I hope you understand the exponent of 10 that gives you 1,000 is 3. 10 times 10 is 100, times 10 is 1,000. The exponent of 5 that gives you 625 is 4. 5 times 5 is 25, times 5 is 125, times 5 is 625. And for all of you computer science folks out there, the exponent of 2 that gives you 1,024 is 10. That's what's called 1K. Now, K usually is 1,000. I know 1,024 is not exactly 1,000, but in the computer science world, it's close enough. And the exponent of 4 that gives you 1/16 is, well, it's got to be a negative to make the 4 a 1/4. And if you square 1/4 times 1/4, you get 1/16. So the exponent is -2. So those ideas, I'm hoping, make perfect sense to you. Now, here's what I want you to see. The exponent of 10 that gives you 1,000 is 3. All we're doing is taking this idea and writing it in a different way. The exponent of 5 that gives you 625 is 4. The exponent of 2 that gives you 1,024 is 10. And the exponent of 4 that gives you 1/16 is -2. So that log just means the exponent of, and then this is the base of that exponent. This is the answer when you raise that base to the exponent, and this is the exponent. The log is an exponent. And so this idea of exponents is why logarithms and exponential functions are always taught together. So if I take this expression, the exponent of b that gives you f of x is x. And the inverse function, well, there's your base. We're switching the answer and the exponent. So this is the answer, and this is the exponent. The log is an exponent. So 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1, etc., etc., etc. 2 to the third is 8. 2 to the fourth is 16. If we reverse the x and y, which is what we mean when we talk about inverse functions, that the exponent of 2 that gives you 1/4, that exponent is -2. The exponent of 2 that gives you 1/2, that exponent's -1. And so this is the number, this is the exponent. This is the number, this is the exponent. In both cases, we are multiplying. And then we have the inverse function here. These are the numbers. These are the exponents that give us those numbers. In both cases, the growth factor is 10. Okay, to do these two, there are two ways to do them. Here's what we do if we read it. This says, what is the exponent of b? Well, I look over here and look at, it's asking what is the exponent of b? Well, there's a b there. What is its exponent? A. And we're done. On the other hand, if you don't see that, here's another way to do this by reading it. This says the exponent of b that gives you b to the a. If things are equal, they're equal, meaning b is the same as b, x or that exponent has to be a. For this one, let's look at this piece up here. This says the exponent of b gives you a. Well, look at this thing up here is an exponent. It's above b. And so it says it's going to give you a. Done. Again, if you don't see it, here's another way to look at it. I could take this expression and say the exponent of b that gives us something, we'll call that x. That exponent is this thing up here. And so there it is. The exponent of b that gives you x is that thing up there. Well, if things are equal, they're equal. Log b, b, the x has to be a. The x has to be a. And then obviously, if we have a function and we have the inverse, the domain of the function becomes the range of the inverse, and the range of the original function is the domain of the inverse. Inverse functions don't change at all. If we look at an example of a typical exponential function, either this one or this one or the other, they all pass the horizontal line test. So in the last unit, that's where we practice graphing exponential functions over and over and over. We saw for the exponential functions, if the exponent is 0, anything to the 0 power gives us 1. For logarithmic functions, since they're inverses, we switch the x and the y, and so we have, if I get 1, the exponent must have been 0. If the number is 1, then the exponent must have been 0. So let's see if this way of reading it helps us. So the exponent of 5 that gives us x is 2. And so 2 goes in the exponent position. The exponent of b that gives us 64, that exponent is 3. The exponent of 3 that gives us 7 is y. So that's how we go from log statements to exponentials. To go the other way, let's look at this. The exponent of 12, and it gives me x, that exponent is 2, isn't it? The exponent of b that gives us 8 is 3. The exponent of pi that gives us 9 is y. I'm hoping that this approach will help you to understand what you're doing instead of just plugging into a formula. So looking at h, which is a little different. The exponent of 6, sure enough 6 has an exponent, that gives us box is this exponent up here. And if things are equal, log log, 6, 6, the box has to be 7. These logs here don't have a base, but the common base, the base that we usually use, is 10. And so if the base is missing, it's actually 10. If you want to write it in, that's fine, but it's understood to be there. Otherwise, it's the same as everything else.